let's begin. And so where we last left off, is nothing working today. All right, so of course, that's an old slide. So there's the reading. The thing to pay attention to for this is the reading. Please make sure you're caught up with the reading. Okay, so where we last left off, we talked about Chebyshev's inequality, and I really wish this thing, nope, wishful thinking doesn't work. It doesn't work. So where we last left off, we talked about Chebyshev's inequality. And as we had discussed, Chebyshev's inequality is a way of putting a bound on this idea of how bad can it get, right? And in this particular case, when we talk about how bad can it get, that idea refers to a random variable, here x, how much can it differ, or how likely is it to differ from its mean by some tolerance with epsilon. So here we have the probability that x exceeds or is different from its mean, mu, by more than some threshold epsilon. That probability, or the likelihood, is no bigger than, less than equal to sigma squared, the variance of that random variable x, divided by epsilon squared, where epsilon, again, is that threshold. So if that threshold is really, really small, that means epsilon is small. So that means epsilon squared is even smaller. So that means you have a small quantity in the denominator, and therefore this probability is going to be pretty big. Now, of course, the probability is at most 1, and certainly it does work out that it's at most 1. And if epsilon is very large, right, epsilon squared, well, it's still smaller than epsilon, but if epsilon's value is larger, that means the denominator is larger, and therefore this sigma squared, that probability tends to be smaller. And so that just says if your error tolerance epsilon is really, really small, meaning that you want your random variable to be close to the mean, to its mean, then that means that probability is going to be very likely, right? Because it's going to be large. And likewise, if you want this tolerance epsilon to be large, right, exceed its mean by more than a large amount, then that probability is going to be small. Right? So this is our so-called Chebyshev's inequality, and we were proving Chebyshev's inequality directly from the definition of variance, which is where we left off. So here we have along the horizontal axis, we have values of our random variable x, and we have its mean, mu here, and we're marking plus and minus epsilon above, I feel a sneeze coming, plus and minus epsilon above and below the mean marked there, and everything corresponding to this probability is this shaded red region, this area under the curve, beyond this epsilon above and below our mean. Okay, so that's where we left off. And when we did so, we took our original expression for variance, sigma squared, and so we expanded it based on the definition for variance. So we have the weighted sum of x minus its mean quantity squared, weighted by probability of x. And so that's just definition of variance, and then we took the bounds on our loop, or the index on our summation, on our loop, and we limited that. And so in the first case, for our formula for variance, that's just the definition, we consider every possible value of x, and now in the second step, we limit our x's, and we limit our x's only to those that exceed mu by this epsilon, by more than this epsilon. So here, in the second case, if we go back to this graph, originally when we compute variance, it's all the x's, and when we have that x such that the x differs from its mean by more than epsilon, we're only referring to the x's that go off in this direction, epsilon below the mean, and all those x's that go off in this direction, epsilon above the mean. Okay, and if we do so, essentially, when we compute our weighted sum for our modified version of the variance, we're computing the weighted sum of fewer things. Because if we're summing together x minus its mean for a fewer number of x's, that's going to contribute smaller to that ultimate count of weighted sums. Make sense? Any questions about this? Again, I really wish I had use of a pen, but that's not possible today. So when we do this, we are making a true mathematical statement. We say this limited version is less than equal to the original version, or if you read this inequality in the opposite direction from left to right, we say the original statement for variance is greater than equal to that modified statement. And the reason why it's greater than equal to is because you're summing fewer things, fewer terms in this weighted sum. And this will always be greater than equal to, because when we look at this term here, right, well, we know probabilities are either 0 through 1, okay, so that's positive. And we know when we square any negative number, it's always positive. So the contributions for each term in the sum are always positive. If you have fewer terms and each term is always positive, therefore that means that the original expression for variance and the modified expression is going to have that greater than equal to relationship. Okay, all right. Any questions about this? So that's where we left off last time. Let's continue forward with this. And what we had done is that we now further took this expression, that limited version of the variance definition, and we said, okay, well, we know we're limiting our x's to only those x's that exceed the mean by more than epsilon. And again, that refers to all the x's here along the red region, and all the x's here going to the left along the red region. So now we say, okay, well, I know if I'm only considering those contributions for weighted sum, which are greater than epsilon away from the mean, if I replace this x minus mu with epsilon, I know that all the things that I add are going to be bigger than that, right? Because if this is exactly x epsilon, that's that 1 point just before, that x just before we're greater than epsilon. So let's depict this visually by going back to the graph. So these are all the x's such that x minus mu are greater than epsilon. So here's my epsilon, right? Anything greater than epsilon, x minus mu, is anything just to the right of this boundary and just to the left of that boundary. So if I call x minus mu exactly epsilon, everything I add here is going to be larger in terms of its difference with mu, right? Okay, so what I can do now for this mathematical expression, if I replace this constricted version of the variance, if I replace that x minus mu with exactly epsilon, well, what do I get? Well, I get epsilon squared here. I'm replacing x minus mu with epsilon, and I still have my times p of x. Okay. And the relationship between this true statement and the previous one, well, the previous true statement up here is greater than equal to that modifying version that has epsilon squared. And the reason why it's greater than is because if I call x minus mu exactly epsilon, well, here, each version of x minus mu, or some version of x, is going to be greater than that. So that means x minus mu, this term, is going to be greater than that epsilon squared term. So therefore, greater than equal to is the right inequality. Now, that is also a true mathematical statement, right? I haven't said anything untrue. And in making any manipulation, as long as you say something that's mathematically true, you can absolutely say that, and nothing is incorrect. So now we have this expression. So let's continue on with the rest of the proof. First, any questions about the previous slide? Any questions about this? So let's continue on. So now, okay, we take this expression we had before. So we started out with the variance. We constrained the x's, and then we chose epsilon as a replacement here and said greater than equal to epsilon squared times p of x. Now, for this expression, that epsilon squared, that's a constant. It does not involve x. This summation, for each term in the summation, the x value changes. And because epsilon squared does not involve x anywhere, that looks like a constant underneath that summation. So we're going to take advantage of the distributive property of multiplication over addition. And we're going to factor out this common epsilon squared in each of the terms represented by the summation. So we can pull this epsilon squared out front. And now we're left with epsilon squared times the summation for all those x's such that x is greater than mu, x minus mu is greater than epsilon for p of x. Okay. Any questions about this stuff? Make sense? All right. So now that we have this expression, we're just going to make another statement. Okay. So here we have a probability. And what this summation says, yes, I'm going to multiply by epsilon squared, but the business end of it, so to speak, is what's happening with that summation. So it says sum together all the probabilities associated with singular outcomes for random variable x. That kind of looks like a complex event, right? We said a complex event is just the unioning together of a bunch of singleton events. If you think of the summation as iterating over a bunch of singleton events, and in this case, those are outcomes for random variable x. So this is really saying, let me compute the probability of a complex event, and that complex event is comprised of the union of a bunch of single events, where each singleton event is the outcome, a single outcome of the random variable. So if I do that, another way of writing this summation term is to say, oh, this is just a complex event called the probability that x exceeds its mean by more than epsilon, which is exactly those two red areas on the left-hand side and right-hand side of the distribution. And then this left-hand side and right-hand side of the distribution has a name. It's called the tails of the distribution. That's just the name. You can think of like an animal tail that kind of goes on, out beyond the body, so to speak, of this distribution. And so really, that summation of the probability of all of the x's for a particular set of x's, those are on the extremes, they exceed our mean mu by more than epsilon, that just identifies the tail. So in essence, what we're saying is this is just a complex event representing the tails of the distribution. Okay? So we write the probability for the complex event, which is just the probability of x minus mu, all of the x minus mu's that exceed, that are bigger than epsilon. Right. Any questions about this? That makes sense? Okay. So really, this is a statement about how bad it can get. You can also talk about it as a statement that talks about the tails of your distribution. Okay. So we have this expression, and one of the interesting things to note is here we started out sigma squared equals something. We're just going to track all of the equalities and inequalities as we go from left to right, from top to bottom, over all of the steps, each of which was a true mathematical statement. And we can collapse this based on what the end points are from where we started through where we finished. So let's do that. So here we have sigma squared equals something, right? That's just the definition. And then we made another mathematical statement, and we said greater than equal to. So we have equals, greater than equal to, greater than equal to, equals, equals. So if we were to write this as a collapsed expression, we could start with our sigma squared. We get some greater than equals to. But because we have these inequalities, we have to preserve those inequalities to maintain this as a true statement. So yes, we have equals, equals here, and those were just some manipulations, right, mathematically. So we would write in summary, sigma squared is greater than equal to this epsilon squared times the probability that x exceeds mu by more than epsilon. That make sense? So let's take a more simple example, and I'll just do it this way. Suppose you had 2 squared, right? 2 squared is equal to 4, okay? So you could write 2 squared as just 4 here. Now 4, you could write greater than equal to 2, right? That's a true statement. So then you could write 2 greater than equal to, say, 1, right? And then if you said 1 is equal to 1 squared, which is just equal to 1. Now, if you were to write the original 4 to the 1, you'd have to preserve that greater than equal to that you encountered along the way. So you could summarize all of that by saying 4 is greater than equal to 1. And that's what we've done here. It's the same exact thing, only instead of using basic numbers, we're using expressions. And on each step of the way, we're using our properties to say if I'm adding together less things, and each of those things is positive, the result is going to be smaller. Okay? And that's basically what we're doing here, what's going on. Any questions about that? Does that make sense? Okay. So now, we can summarize it as the following expression. Sigma squared is greater than equal to our epsilon squared times probability that x exceeds mu by more than epsilon. Now, of course, when you have this inequality, you can read it left to right. Sigma squared is greater than equal to epsilon squared probability of. Or you can read it from right to left, because it doesn't matter which one is on the left and on the right when you have equality. So if we read it right to left, we could read epsilon squared times probability of is less than equal to sigma squared. So let's just write it that way, reading it from right to left. And we just rewrite that. And so we have our epsilon squared probability that x exceeds mu by more than epsilon is less than equal to, sometimes pronounced no more than, less than equal to or no more than sigma squared. Does that make sense? Any questions? So that last step, all we're doing is just taking our inequality that we wrote down by collapsing each of these steps, respecting these inequalities that we had along the way, and we're just taking the final collapsing one and reading it right to left and writing it that way. Okay. So now, let's perform a little bit of algebra. Let's divide both sides of this inequality by epsilon squared. So we want to bring epsilon squared, as people call it, to the other side of the inequality. So we divide both sides by epsilon squared. The epsilon squared over here goes away, and we get 1 over epsilon squared on the right-hand side of the inequality. Okay, so now what we're left with is exactly, whether we collect the squaring or not, is exactly what our original expression was for Chebyshev's inequality. Okay. Any questions about this? Make sense? Yes? Yes. So we start out with this. So if I divide the right-hand side by epsilon squared and the left-hand side by epsilon squared, this one cancels out, and I have sigma squared times 1 over epsilon squared. And I get that result. So now, of course, this is just cleaning up. You can leave it like this or clean it up a little bit if you want to. It's the same expression. But you could say, okay, well, I have something squared over something squared. I could just take the division first before the squaring, and it's the same result. Okay. Sometimes people write it as sigma squared over epsilon squared. Sometimes people write it as sigma over epsilon quantity squared. It's the same quantity. Any other questions? Make sense? So this actually works in practice. In fact, if you wanted to, I'm not saying you should, but if you wanted to, you could take like the brain wave data set, EEG data set, and try it out for any of those columns. And each column, as I said, is a random variable. You could actually try it out, and it does work. In fact, we'll be using Chebyshev inequality at a later time during this semester. So, and that's what we get. All right. So let's take a look and segue, and we'll spend the rest of today talking about distributions in general. Now, we started out talking about events and their probability, and we said these events have probabilities associated with them. And then we segued to something called random variables, and we said a random variable is some measurement of the event. And we use that to motivate the idea of a distribution. And we said we take all the outcomes of the random event and the probabilities these outcomes can take on. We can write them in tabular format, and that tells us about the behavior of this random variable, the aboutness, as we call it. And we said that with a distribution, we can plot it as a graph, and the shape of this graph tells us about the behavior of the system. We can talk about its center, the mean. We can talk about its dispersion. If we have multiple variables, as we've seen or have on the assignment, project 2 that's due, we said we can look at the coupling between variables through covariance and correlation. So let's talk a little bit more about distributions. Now, over time, mathematicians and statisticians study number systems, and they looked at the distributions that govern those measurements. And we saw this with some of the observations we did. If you had a dodecahedron coin flip game or a dodecahedron gambling game, if you chose 2 events, the event 1 through 6 complex event and the event 7 through 12, your observation would be that for each of those complex events, the probability would be 50% for the 1 through 6 complex event and probability 50% for the 7 through 12. And so in essence, while it's a different game, the stochasticity is exactly like a coin flip, which only has 2 sides. Likewise, if you had a die and your 2 complex events were 1 through 3 and 4 through 6, it would behave just like a coin flip. So this is one of the observations people have made over decades, and statistics is probably at least 100 years old in its modern form. And these descriptions, rather than kind of reinventing the wheel each time, people say, hey, let's put these things in standard forms. The structure of stochasticity, it acts like a coin flip. And now, if we do that, we can prove things about it once. And now, whenever you want to use these tools, instead of having to reinvent the wheel each time, you now ask the question, is the stochasticity for the system that I have, what does it most resemble? And if it resembles certain properties of these standard study distributions, then I can just use that distribution instead of having to derive everything from scratch each time. So these descriptions are widely applicable to systems. These that share properties, right? And these standard distributions are described as these functions, and they're also described by scenarios that look at the structure of your stochasticity. So what do we look at for the description? We look at system properties. We look at functional descriptions and how that function behaves, and we'll talk about two of them. We also use these standard descriptions that the statisticians have developed to describe families of distributions, families of means or ways of behavior for stochasticity. And so there are two major families. One called discrete distributions, and those are descriptive of systems measured by random variables that take on either a finite or a countably infinite set of values, or so-called continuous distributions, and those are systems whose random variables have outcomes that are on the real number line. They're uncountably infinite. And so let's take a look at some of these. Now the first two are relatively simple, and the first one is called a Bernoulli distribution. Any system that matches the properties of a Bernoulli distribution, you call that random variable a so-called Bernoulli random variable. And likewise, the trial or the experiment that you perform is called a Bernoulli trial, a Bernoulli experiment. And so you have a random variable for a Bernoulli distribution if your random variable takes on one of two possible values. So you could call it as your sample space omega has cardinality 2, right? This is what a coin flip does. Or selecting male or female that behaves exactly like a coin flip, has two outcomes. And so anything that has a property, any system, where you have two possible outcomes, you could certainly pass or describe as a Bernoulli random variable. So a coin flip, picking a co-ed team consisting of men and women, those are two choices. And therefore, it matches this structure, this behavior of a so-called Bernoulli random variable. So you have a random variable, and it takes on two values, plus, minus, 0, 1, success, failure. This is called a Bernoulli random variable. Now, in the book, there's a typo. It should say Bernoulli random variable, not Bernoulli distribution. The random variable is the measurement that takes on an outcome. The distribution is the catalog or graph of all the possible outcomes associated with their probabilities. Any questions about this? Does that make sense? So let's say you're trying to describe something, and maybe the question is, you're going to select whether someone wants pasta or pizza, right? There are only two choices. That acts like a Bernoulli random variable. So when you have an experiment or a scenario, and one of the questions you ask yourself is, does this scenario or experiment take on one of only two values? If so, it's a Bernoulli random variable that best describes the stochasticity of the system that we study. So a Bernoulli experiment is called Bernoulli. It's named after a person that developed it, Jacob Bernoulli. Right? So you develop one of these at grad school, do some research, develop one of these, you can call it whatever you want. Typically it's after your last name. Okay. I hope you do. So I can say, I had that person in my undergrad class. All right. So let's take a look at the probability. So a Bernoulli distribution has two outcomes, and how the Bernoulli description is that you have two outcomes, 0 and 1. One is the so-called positive outcome, and 0 is the other outcome. I don't want to say negative, because that's too confusing. So we have a 1 outcome and a 0 outcome, two possible states that we can observe for a random variable. That can be heads or tails, male or female. It's all Bernoulli random variables. complex events 1 through 3 versus 4 through 6, it's all Bernoulli random variable described by a Bernoulli distribution. So it's such that the outcome of one alternative, let's call it the one alternative, the probability of a 1, is equal to some value p. Now p is a probability, and it can be between 0 and 1. It could be exactly 0. It could be exactly 1. It could be between 0 and 1. It doesn't matter what it is. It is just some proportion representing a probability. So for a Bernoulli distribution, the probability of one of your two outcomes is p, and the probability of the other outcome, the 0 outcome, p of 0, is 1 minus p, right? Now, of course, we say 1 minus p, you could surmise that by saying, oh, well, I have two outcomes. Law of total probability says the other outcome is going to be 1 minus the first outcome. So in Bernoulli distribution in the literature, 1 minus p is often described by a variable named q, right? So some might say p and 1 minus p, some might say p and q, right? So we have p as the outcome or the probability for the first outcome, and 1 minus p, also known as q, is the probability of the second outcome. So that's what governs a Bernoulli distribution. So let's say, for picking male and female at DSU in 2018, it was 60% chance of picking female if you picked randomly a selected person, and 40% picking male, right? So in that case, if it's gender for a student in 2018 at DSU, probability of 1 would be 0.6, and probability of 0 would be 0.4, okay? And so your quote-unquote coin flip, if you will, doesn't have to be 50-50 to be Bernoulli. You just have to have two outcomes. The first outcome has probability p, and the second outcome has probability 1 minus p, also called q. Okay. Any questions about this? Yes?
How do you use that first one to try and figure out
It doesn't matter. It does not matter. Now I'm choosing p 1 to be a certain outcome. You could choose, in the case of gender, you could choose male is 1, female is 0, or you could choose female is 1 and male is 0. You just have to state that in the definition, and it's still a Bernoulli distribution. Any other questions? But the important part, and I'm glad you asked that, the important part is when you describe it, you have to be consistent, right? Because if you say one outcome is 1 and the other is 0, you can't later on switch it because that'll be confusing. You'll be talking about the wrong thing. Okay. So let's take a look at the variance. So that's the probability. Let's take a look at the, and that's the, very far ahead. Let's take a look at the expectation first. You have to do expectation before you do variance. Okay, so there's our definition for expectation. Expectation of a random variable doesn't matter what the distribution is. In this case, we're going to talk about Bernoulli. Expectation of our Bernoulli random variable, x, is equal to the weighted sum of each of the outcomes of x, and x is going to take on an outcome of 1 or an outcome of 0, times the probability of that outcome. So let's fill this in and calculate what the expectation is for Bernoulli random variable. So if it's a 0 outcome, it's 1 minus p. So we write 0 as the value x. P of x is 1 minus p, because that's what we defined above. Now, the other outcome is a 1. So if x is 1, that's a 1. And the probability of a 1, we defined up there as p. So we're just plugging in for expectation the values that we have given our definition. So if we do that, of course, well, the first term cancels, because 0 times anything is 0. And we're left with 1 times p, which is just p. So for a Bernoulli random variable, the expectation is going to be exactly p, where p is the probability. So if you had, for example, in 2018, 60% of the student population is female, 40% is male, and you were asked what is the expected proportion of females that you would pick, well, it's a Bernoulli random variable, so you just write p, right? It sort of saves you the step. And you can prove that it's a Bernoulli random variable because you say, well, my outcomes are only 2 states, male and female, and I have a probability proportion for female is 60%, 0.6. So now I know it's a Bernoulli, I know what my p and my 1 minus p are, so now I just make use of this property that has already been proven. And so statisticians have done this for very many types of stochasticity, things that deal with time, things that deal with real values, things that deal with phases of execution, all sorts of things. And so now, going forward, we will learn the properties that categorize certain structures as a certain type of distribution, and then we'll prove the expectation and the variance, and then just go forward with showing those properties. And then we'll use these things in certain examples to try to make statements about systems. Okay? All right, any questions about this? Make sense? Okay. So now the other description about the distribution, because remember, our whole reason for using so-called summary statistics is that it's too tedious to list out a whole table, and sometimes, we have a graph, we need to characterize the shape, and one way to characterize a graph representing a distribution is to look at the center, namely the mean, and look at how dispersed or spread out it is, i.e. the variance. So now we'll look at the variance of this Binomial distribution. So there's our equation for the variance, and I almost forgot, Greek letter mu is the shorthand for the expectation, so mu is equal to p for Bernoulli random variable. So let's look at the variance. So there's our equation for the variance. The variance, or the variability or dispersion or spread of the distribution for the Bernoulli variable is equal to the weighted sum. And so our weight, again, is the probability, so there's times p of x. And the thing that we're weighting are the differences between each outcome, x, of a random variable and its mean, p of x. So here we have x minus p of x, and we square it because we're concerned about the magnitude and not about the direction, okay? So that could be positive if x is greater than p of x, or it could be negative if x is less than p of x. It doesn't matter what that positive or negative is. What matters is the magnitude, so we square it. So we have x minus e of x quantity squared times the probability of x, and we weight that and sum together for all such values of x. So let's go ahead and do that. The first thing we're going to do is we're going to replace e of x with its summary, mu. Mu is equal to e of x. So we do that, and we have an x minus mu quantity squared times p of x. Now, we're going to use the FOIL rule to multiply that out. And so we have x squared, right? Because that's x minus mu quantity squared. We have x squared. We have mu squared. And then we have minus, right? Because that's a minus sign, 2 times the cross term. So we get 2 mu x, because there's a mu, there's an x. And we have that negative sign. So we have a minus 2 mu x. So now we take that application of the FOIL rule, and we have that in parenthesized expression, or multiplying that times p of x, right? So we're going to distribute that multiplied by p of x, take advantage of the distributive rule, multiplication over addition. And we're going to multiply that p of x by the first term, x squared. We're going to multiply that p of x by the second term, 2 mu x. And we're going to multiply that p of x by the third term, mu squared. So we do that, and we can also, when we do that multiplication, we can reassociate those individual terms and bring them each under its own summation symbol. Okay, so we take our p of x, we distribute that multiplication x squared, so p of x times x squared, or x squared times p of x, under its own summation. Likewise, we take our p of x, we distribute that multiplication to that second term, so that's a minus 2 mu x p of x, and we have that under its own summation. But in putting that under its own summation, we make the observation that 2 mu does not involve x, so we can factor that out of each of those terms. So we have a minus 2 mu summation of x times p of x. And then lastly, that third term, p of x, we multiply that times the mu squared. So we have mu squared p of x under its own summation. That mu squared does not involve an x, so we can factor that out, taking advantage of the distributive rule. We can factor that out from under the summation, and we have for that third term mu squared times summation of p of x. Any questions about this? Make sense? No questions? So now, we take this expression, and we make some observations. Well, here we have x times p of x under summation. That's exactly the expectation. So we can replace that with a mu, right? It's exactly expectation or mu. So we replace that with the mu, we have 2 times mu, which is mu squared. Likewise, with this third term, we have the sum over all values of x for p of x. Well, we know the law of total probability says that if you add together the probabilities of all the values or outcomes of a variable, that's just 1, right? So we can replace that summation on the third term. We can replace that with a 1, right? So that's this mu squared times 1. So let's do that. So we replace this with mu, right, which is this e of x, 2 times mu times mu. Replace this with a 1, so we're just left with a mu squared. Now 2 times mu times mu is just mu squared, and you note here we have minus 2 mu squared plus mu squared. That's the same as minus mu squared. So we're going to add those two terms, and we're left with x squared p of x minus mu squared. Okay? All right. Any questions about this? Question? Any questions? Make sense? Okay. So now that we have this expression, let's do a little bit of substitution. So again, we have our values of x, and as we said, x in a Bernoulli distribution can take on 2 values, a 1 or a 0, right? If it's a 1, the probability is p. If it's a 0, the probability is 1 minus p. So we're just going to substitute. We're going to substitute for x equals 1, so that would be 1 squared times p, right? And then we're going to substitute for 0, that would be 0 squared times 1 minus p, right? And then we have this minus mu squared turning out there. So let's make that substitution. Our mu, as we said before, when we did expectation, is just p. So let's do that substitution. So we have our minus mu squared. Mu is just p, so mu squared is p squared. So we have a minus p over there here. So next, let's take care of the summation. We have x iterates through all values of x. So it's 0 squared for the 0 value. The probability of a 0 is 1 minus p, so we multiply by 1 minus p, so that takes care of 0 into the summation. And then for the 1, right, we have 1 squared substituted for x, and the probability of 1 is a p. All right, so we'll make that substitution. So now 0 squared is just 0, and we're left with 1 squared, which is 1. So we have 1p minus p squared. So we have p minus p squared. We factor out the common p. We're left with p times 1 minus p. And we just said that 1 minus p sometimes is called q. You could absolutely, with no problem, leave it as 1 minus p. But typically, in many parts of the literature, when you see some mathematical expression, they try to always minimize it as much as possible, make it as simple or less text as possible. So I'm going to go ahead and substitute q for 1 minus p, and so we get pq. Okay? And so the variance of a Bernoulli random variable is just pq, where p is the probability of the 1 outcome, and q is the probability of the 0 outcome. And it doesn't matter which one you make 1 and 0. If it's selecting male and female, you can make selecting male 1, selecting female, that probability, the 0 outcome, or vice versa, female is 1 and male is 0. Right? It doesn't matter which one. But what does matter is recognizing the fact that if you have a 2A outcome, and there's a probability associated with one thing, and a probability associated with other, that it's a Bernoulli random variable, and the properties of it is that the expectation is equal to p, and the variance, sigma squared, is equal to p times q. Okay? All right. Any questions about this? Does that make sense? And so rather than having to do this, again and again and again from scratch, they've already done the work for you. And now the task at hand is trying to recognize for a system that you're given, which distribution properties best match this scenario for the system you're given. Does that make sense? Questions? So that's the Bernoulli distribution. Another important distribution that's been studied is the so-called binomial distribution. And a binomial distribution takes your Bernoulli 0-1 outcome and it puts it together into a string of zeros and ones. And so we have n many Bernoulli tribes. So there's the first trial that can be 0 or 1, there's the second trial that can be 0 or 1, there's the third trial that can be 0 or 1. So imagine a scenario where you're asking somebody, let's say a group of 10 people, which type of dish do you want? Do you want the pasta or the pizza, right? So, first person could say pasta or pizza. Second person could say pasta or pizza. Third person could say pasta or pizza. And then you might want to know, what's the probability that out of those 10 people, maybe 6 of them are going to say pasta, right? You might want to know that probability. That's exactly what binomial distribution measures. And so binomial distribution is related to the probability. For binomial, you have 0, 1 outcomes, but you have a string of n many experiments or trials. So n many times you're going to ask the question or measure something. Each one of those n many times could have a 0 or 1 outcome, 2 possibilities. The probability associated with that random variable gives you a distribution, and that is a so-called binomial distribution. And it's called a binomial distribution because the leading coefficient is called a binomial coefficient, which I'm not going to get into for this class. So the probability for a binomial distribution, if you have n many trials, where each trial has a 2-way outcome, a Bernoulli trial, that the number of 1 outcomes or positive outcomes is going to equal x. So you have n trials, and you're trying to see what's the probability that x of these trials is going to be my positive outcome. So that could be I flip a coin 10 times. What's the probability that 6 of them are heads? I asked a question about pasta or pizza. What's the probability for 10 people? And I want to know the probability that 6 of them said pasta, right? So that is probability that random variable x for a binomial random variable takes on a value of x, like 6, is equal to n choose x, where n is the number of trials, x is the number of desired positive outcomes, so n choose x, times probability of x, probability of the positive outcome raised to the x power. And if you think about it, if you have x many positive outcomes, for each of those outcomes, there's a probability of p associated with it. So like you're saying, p times p times p times p times p, x many times. And then the remaining outcomes are the negative outcome of 0. So that's q, which is 1 minus p, q times q times q times q times q for the remaining n minus x. So if n was 10 trials, and you're interested in probability of random variable x equals 6, that would be 10 choose 6, p to the 6th power, q to the 10 minus 6 power, or q to the 4 power. Okay? Any questions about this? That make sense? Okay. And so this is a so-called binomial distribution, and this works with all sorts of things. So let's say, you want to know what's the probability if I picked people at DSU, picked 10 people without any preference in 2018, what's the probability that the 10 people maybe I surveyed would be female? What's the probability that 6 of the 10 would be female? Well, you can actually compute that probability. And the reason why someone might want to know that is if you have a survey result, you analyze the probabilities associated with certain types of outcomes, and you can use that to weight the results of your survey. Because in the case of DSU, because the female population in 2018 is 60%, right? It's much larger than the 40% for male. So if you took a survey, you want to know, based on that outcome, the proportions are going to impact what your survey results are. And so it's very important to know such probabilities. And so in that case, we would use a binomial distribution for those probabilities. Okay? Any questions about this? So if you're given a system and you study the system, you say, aha, well, what I'm measuring, it kind of looks like n many observations, each of which can be 0 or 1. You can describe that with a binomial distribution. Okay? All right. Any questions? So now that we know it's a binomial distribution, there's the probability mass function, because this is a discrete distribution, right? Countably infinite, or countable rather, number of different outcomes. And this is this mass function that gives you the probability. So now, of course, The other thing you need to do, once you know it's a binomial distribution, you might want to know what its mean is, its center, and what its variability is to summarize it, right? Because you don't want to have to go out and plot it. So again, the expectation, we compute expectation as the weighted sum of x times p of x, sum the overall value of x. And the variance is just the weighted sum over all values of x minus its mean, so x minus e of x quantity squared times p of x. So the expectation is NP, and the variance is NPQ, and I'll leave it to you in the book to do that. Now, of course, don't just look at it. You know, there are other sources. There's Khan Academy, and there's stuff on YouTube, and there's publications out there. But do it yourself. Get used to doing these manipulations yourself with pencil and paper, pen and paper, because it's a lot more memorable if you retain more if you actually do it yourself, so-called kinesthetic learning. Okay. So I'll leave that to you in the book as an exercise. We can certainly do it in class, but I really want you to go off and try this yourself. Okay? All right. Any questions about this? Make sense? All right, so we have our two first distributions. We have the Bernoulli and we have the binomial. They're both related, and we'll further on Thursday with studies of other distributions. We'll all kind of build upon them. Okay. All right. No questions? Last questions? Expected more questions. All right, so I guess we'll just end now and early. So I will see you on Thursday.